Chapter 8 continued, Electron Configuration and Chemical Periodicity, Section 8.4, Atomic Properties and Chemical Reactivity. In this section, we will see how the properties we just discussed affect or influence metallic behavior. We will also use atomic properties we just discussed to determine the type of ion an element can form. Metals are typically shiny solids with moderate to high melting points. Metals are good conductors of heat and electricity and can be easily shaped. Metals tend to lose electrons and form cations, meaning they are easily oxidized. Metals are generally strong reducing agents. Most metal form oxides, which are basic in aqueous medium. This slide shows the trend for metallic character or behavior. Metallic behavior or character decreases as we move from left to right across a period of the periodic table. This makes perfect sense, seeing how metals are located on the left side of the periodic table and nonmetals are located on the right side of the periodic table. Metallic character will also increase as we move down a group. Metals tend to lose electrons during chemical reactions because of their low ionization energies, and nonmetals tend to gain electrons because of their large electron affinity. In Figure 8.21, this illustrates how an increase in metallic character can affect both the physical and chemical properties of metals. Moving down Group 5A, we see an increase in metallic character and thus a decrease in ionization energy. Nitrogen at the top of the group tends to form an anion, and bismuth at the bottom of the group tends to form a cation. Moving left to right across period 3, we see a decrease in metallic character and an increase in ionization energy. Elements at the left of period 3 tend to form cations, and elements at the right of period 3 tend to form anions. What is the driving force for metals to lose electrons and form cations, and for nonmetals to gain electrons and form anions? Or better yet, why do Group 1A metals lose 1 electron while Group 2A metals lose 2 electrons? Why do Group 7A nonmetals gain 1 electron while Group 6A nonmetals gain 2 electrons? The answer is because atoms lose and gain electrons in order to adopt a noble gas configuration. By acquiring a noble gas configuration, the atoms acquire the same stability as a noble gas. Noble gases are very stable because their outermost energy levels are completely filled. This is the driving force behind the atoms losing and gaining electrons. They are all trying to acquire a noble gas configuration. When sodium loses 1 electron and magnesium loses 2 electrons, both of these ions have the same number of electrons as neon, or 10 electrons. By losing electrons, both sodium and magnesium now have a filled outermost energy level just like neon. On the other hand, oxygen tends to gain 2 electrons to form an anion, and fluorine will gain 1 electron to form an anion as well. They do this so that they will have the same number of electrons and the same electron configuration as neon. These ions are said to be isoelectronic with neon. Isoelectric is when atoms or ions have the same number and configuration of electrons as another species. Our next topic of discussion is the acid-base behavior of oxides. What is an oxide, you might ask? An oxide is a metal or a nonmetal in a compound with oxygen. Metal oxides exhibit different acid-base properties than acidic oxides do. Metals tend to transfer an electron to oxygen to form ionic metal oxides. Metal oxides produce the hydroxide ion when placed in water and thus are considered to be basic. Nonmetals tend to share electrons with oxygen, forming covalent nonmetal oxides. Nonmetal oxides produce the hydrogen ion when placed in water and thus are considered to be acidic. Some metals and metalloids, such as aluminum, have the ability to behave as an acid or a base in water. Such oxides are said to be amphoteric oxides. Figure 8.24 shows the trend of acid-base behavior of both metal and nonmetal oxides used in period 3 and group 5A. As we move left to right across period 3, notice the acid-base behavior of these elements changes from basic to acidic oxides. The more metallic character, the more basic the oxide. Notice what happens as we move down group 5A. We go from acidic oxides to basic oxides as the metallic character increases. So far we have focused on the reactants, the atoms in the process of electron loss and gain. Now we focus on the products, the ions, considering their electron configuration, magnetic properties, and sizes. Elements at either end of a period gain or lose electrons in order to fill their outermost energy levels. The resulting ion will have a noble gas configuration and is said to be isoelectric with that noble gas. Remember, isoelectric is defined as having the same number and configuration of electrons as another species. Two illustrations are shown on this slide. When sodium loses one electron, it forms the sodium cation, which has the same number of electrons and the same electron configuration as neon. Chlorine gains one electron to form the chloride ion, which has the same number of electrons and the same electron configuration as krypton. Do you see this? This is figure 8.25, and it shows us the main group elements whose ions have noble gas configurations. With the exception of aluminum, metals of group 3A to 5A do not form noble gas configurations. Instead, they form cations with two different stable configurations. The first is a pseudo-noble gas configuration, which is attained when a metal atom empties its highest energy level. The ion attains the stability of an empty NS-NP subshell and a filled N-1D subshell. Please see the pseudo-noble gas configuration for tin on the middle of this slide. The second is an inert pair configuration. Here a metal may lose only the NP electrons to attain an inert pair configuration. The ion attains the stability of a filled NS and N-1D subshell. Please see the inner pair configuration for tin at the bottom of this slide. Now it's time to put all of our newly acquired knowledge to work and work through sample problem 8.6. Sample problem 8.6 wants us to write electron configurations for the formation of main group ions from their elements. Remember, metals lose enough electrons so they have the same electron configuration as the noble gas that is usually behind the metal. Nonmetals tend to gain enough electrons to have the same electron configuration as the nearest noble gas, usually in front of the nonmetal. Let's work through parts A together, and then you can work through parts B and C on your own, as well as the follow-up problem. Part A is iodine, and iodine is in group 7A, which is one electron away from a noble gas configuration. Our strategy is to write the electron configuration for the element of interest and then have it gain or lose the appropriate number of electrons until it has the same number of electrons as its nearest noble gas. Then we will rewrite the new electron configuration for the ion that forms. The electron configuration for iodine is krypton in brackets 5s2 4d10 5p5. Iodine only needs one more electron in its sp sublevel to have the same electron configuration as neon. Now we add the electron and form the iodide ion, and now when we rewrite the electron configuration for the iodine ion, we see that it now has a full outermost energy sublevel. The new electron configuration for iodine is krypton 5s2 4d10 5p6. That is the correct electron configuration, condensed electron configuration for iodine. Notice that we did not say that the new electronic configuration for iodine is xenon in brackets, even though iodine now has the same electron configuration as xenon. Remember, when we are writing the condensed electron configuration, we use the noble gas that is behind the atom of interest and not in front of the atom of interest. So please work through parts B and C on your own before moving on to the next slide where you can check your work. Okay, so here is the complete answers for A, B, and C. So please compare your answers to the answers shown here, and then let me know if you have any questions or concerns. When we are writing electron configurations for elements, did you ever wonder why the 4s sublevel is filled before the 3d sublevel and why the 5s sublevel is filled before the 4d sublevel? Also, when forming cations, why do we remove the 4s electrons before we remove the 3d electrons? Well, now it is time to answer these questions. The 3d orbitals are empty in elements at the beginning of period 4. Because the 4s electrons penetrate closer to the nucleus, the energy of the 4s orbital is lower in elements potassium and calcium, therefore the 4s orbital is filled first. But at atomic number 21, now the 3d orbitals are starting to fill up with electrons, and these inner electrons are attracted by the increasing nuclear charge, so they start to shield the 4s electrons. As a result, we have a crossover with the 3d sublevel becoming lower in energy than the 4s. For this reason, the 4s electrons are removed first when the transition metal ion forms. In other words, electrons with higher values of N are removed first. For main group metal ions, the highest N value electrons are removed first, last in, first out. For transition metal ions, the highest N value electrons are also removed first, but it's first in, first out. Let's look at the magnetic properties of transition metals. Remember that the electron spin generates a tiny magnetic field that causes a beam of hydrogen atoms to split in an external magnetic field. Only atoms, ions, or molecules that have one or more unpaired electrons in its electron configuration are affected by an external magnetic field. A species with unpaired electrons exhibit paramagnetism and is attracted to an external magnetic field. A species with all of its electrons paired exhibit diamagnetism and is not attracted to an external magnetic field. The magnetic behavior of transition metals can provide evidence for the electron configuration of a given ion. Titanium-2 ion has 2 unpaired electrons and is paramagnetic, providing evidence that the 4s electrons are lost before the 3d electrons. Sample problem 8.7 would like us to use condensed electron configurations to write the reactions for the formation of each of the following transition metal ions. Then determine if the ion will exhibit paramagnetism or diamagnetism behavior. What is our strategy? First, write the condensed electron configuration for each atom. Remove electrons beginning with the ns electrons and determine if there are any unpaired electrons remaining. Okay, so that is our strategy. Please work through this problem on your own before moving on to the next slide where you can check your work. Here are the solutions to sample problem 8.7. Please compare your answers to the answers shown on this slide. If you did not come up with the correct electronic configurations, please send me your work using the email system built into the course. I will see if I can help you figure out why your answers differ than the ones shown here. Please be sure to work through the follow-up problem before moving on to the next slide. Cations are smaller than their parent ion. A cation forms when electrons are removed from the outermost energy level, decreasing the amount of electron-electron repulsion. The number of protons remain the same. Therefore, the remaining electrons are pulled closer to the nucleus, decreasing the size of the cation. Anions are larger than their parent ion. An anion forms when electrons are added to the outermost energy levels. Once again, the number of protons remain the same. However, there is a greater amount of electron-electron repulsion and the size of the ion increases. The size of the cation decreases and the charge increases. An isoelectric series is a series of ions that have the same electron configuration. Within the series, ion size decreases with increasing nuclear charge. The atomic radius is an estimate of the size of an ion in a crystalline ionic compound. In this slide, the radius of the cation R+ and the radius of the anion R- each make up a portion of the total distance between the nuclei of adjacent ions in the crystalline ionic compound. Using the relation between effective nuclear charge and atomic size, we can predict the size of an ion relative to its parent atom. Figure 8.29, which is shown on this slide, shows the radii of some of the main group ions relative to their parent atom. From this slide, we can determine that ionic size increases as we move down a group, but the trend is a little bit more complicated moving across a period. What we have noticed with ionic size is that ionic size decreases across a period, but increases from cations to anions. Ionic size also decreases with increasing positive or decreasing negative charge in an isoelectric series. Ionic size decreases as charge increases for different cations of a given element. In sample problem 8.8, we are asked to rank each of the given set of ions in order of decreasing size and explain our rankings. Let's work through part A together. The ions in part A are calcium 2+, strontium 2+, and magnesium 2+. First thing we need to do is to locate these ions on the periodic table and then apply the ideas presented in this section. All of the ions in part A are from group 2A. According to the ideas in this section, the size of ions tend to increase as we go down a group, which means strontium 2+ is larger than calcium 2+, which is larger than magnesium 2+. So this is our order of decrease in size. Strontium 2+ is greater than calcium 2+, which is greater than magnesium 2+. And our explanation is the size of ions increase as we move down a group. Now work through parts B and C on your own, in addition to the follow-up problem. After you have completed parts B and C, move on to the next slide where you can check your work. Okay, so compare your work to the work shown here, and then hopefully you came up with the correct ranking of the ions. If not, please let me know and I will try to help you figure out why. This is the end of week 12, which covered the materials from chapter 8. Work as many of the assigned end of the chapter problems you feel is necessary for you to master the material presented here. When you're ready, move on to the weekly quiz. Even though it says to perform the laboratory assignment and to take the laboratory quiz, there are no laboratory assignments for week 12. After you have completed the weekly quiz, please move on to week 13. In week 13, we will discuss the materials from chapter 9 titled Models of Chemical Bonding.